Great, thanks a lot. So firstly, thanks to Lorenzo and Eric for this wonderful introduction on carpet X. And yeah, we would see a bit more about carpet X and on Asterix later in the tutorial. But stepping back to carpet-based codes, today I'll be talking about the new code, GRMHD code Spritz. And firstly, I would like to thank the organizers for giving me this opportunity. And just to tell you that Spritz is essentially a Prosecco-based cocktail, which originates from the northeastern part of Italy, dating back to 1800s, I guess. And this is what you see on the right side of the slide. And the Spritz code has been developed as a collaborative effort involving different people, including myself and my supervisor, Dr. Riccardo Ciolfi, and Federico Cipolletta, Lorenzo Noggi, Professor Bruno Giacomazzo, Eduardo Giangrandi, Beatrice Guidici, Wolfgang Gaston, Rahim Mathur, Lorenzo Sala, and others. In this talk, I'll be giving you just a very brief introduction on Spritz and also some of the latest ongoing Spritz-related work. So to start with a bit of an introduction, in order to address some of the open questions in different astrophysical scenarios, such as core collapse supernovae, evolution of proto-neutron stars, accretion disk systems, or even neutron star mergers, or even jet formation, we understand that we do need GRMHD simulations. And they play a fundamental role. And this was also emphasized very well in Professor Campanelli's talk on Monday. And to give you a bit of a quick introduction, to perform such simulations, we need numerical relativity, which allows us to solve the nonlinear Einstein equations coupled with matter fields. And the standard approach is the basic 3+1 technique. And this was, I think, well discussed in Professor Wittek's talk on Tuesday. So I will not go into detail, but just to mention that, okay, for the space-time evolution, usually state-of-the-art codes use BSSN formulation, which is provided, for instance, by the Maclaurin-Thorne of the Einstein Toolkit, while the matter fields are the GRMHD evolution is based on the Valentia formulation, which is widely adopted by the different GRMHD codes, such as GRHydro, Illinois GRMHD, and also by Spritz. So the Valentia formulation considers the GRMHD equations as a set of first-order system of equations, which are written in a flux conservative form, where you have alpha as the lapse, and gamma is the determinant of the tree metric, and u is the state vector, or the so-called conserved variables. F stands for the different fluxes, and S stands for the source sum. So I don't go into details of how this Valentia formulation was derived. You can find in literature. Just to mention here that the primitive variables are the so-called rest mass density, fluid three velocities, epsilon is the specific internal energy, you have electron fraction, and using those you can redefine these conserved variables, such as conserved density, dense, S-con, tau, and also the densitized magnetic field and electron fraction. Now, typically, GRMHD codes work under the assumption of ideal MHD, which consider the fluid to be perfectly conducting, and which implies that the co-moving observer does not measure any electric field. So one can then rewrite the Maxwell equations solely in terms of the magnetic fields in the co-moving frame, which can then be also separated into the divergence precondition, as well as the induction equations for B. One can also choose to evolve instead the vector potential, and then eventually compute B from the curl of A. And now to close the system of GRMHD equations, we require an equation of state. So depending on the astrophysical problem in hand, there exist different kinds of equations of state in the market, starting from the simplest analytical ones, which could describe the behavior of an ideal fluid or a polytropic gas, to a more complex one, which have temperature and composition dependence and come in 3D tabulated forms. And to solve such equations on a numerical grid, we need state-of-the-art numerical techniques in order to effectively capture the different mechanisms, such as shocks and discontinuities that might occur in the simulation. So the typical approach is to incorporate high-resolution shock capturing schemes, which typically involve two-step process. First, you implement or employ a reconstruction method that interpolates the grid variables to the left and right sides of the grid cells, from the cell centers to the cell interface. So such reconstruction method, like the second order min-mod or third order piecewise polytropic reconstruction methods. And then the second step would be then you employ approximate Riemann solvers to solve this Riemann problem generated at this cell interfaces and compute the fluxes at these cell interfaces. So just to give you a quick idea of a typical code workflow. So first, we initialize the primitive variables at each grid points, and then you do a primticon to compute the conserved variables from the primitives. And then you evaluate the source terms using the finite difference schemes in hand, and also evaluate the flux terms using the high resolution shock capturing schemes that I mentioned before. And then source minus flux gives you an ODE for conserved variables, and which can then be solved using a time integrator, such as a Runge-Kutta-4. And this gives you the conserved variables for the next time step. And then you use something called as a con to prim to compute the primitives from the evaluated conserved variables at the next time step. This is just a very typical, but of course I'm missing all the various details, but just to give you an idea of what happens in such a GRMHD code. So this slide, in this slide, I compared some of the features of the different some of the GRMHD codes that work with the Einstein Toolkit framework. And I've stolen this slide from one of the talks of Professor Giacomazzo. So here you see, based on the different features that are available or implemented in these codes, you can see that, for instance, we have Illinois GRMHD, which, for instance, implements or evolves B field based on a vector potential prescription, which is staggered. And there's also some interesting development going on, and which Leo will talk about in his in the next talk. So do stay tuned for that. And I'm quite looking forward for that too, and probably all this green would orange would turn to green. And for the case of Spritz, I take, and in the next slides I talk about these different features that I mentioned here. So Spritz is essentially derived from the parent code Whiskey MHD, and it implements evolves a vector potential which is staggered. So what does that mean is, so if you take a numerical cell here, which is shown on the right, you have the hydro variables, for instance, defined in the cell centers, while you define your vector potential variables on the cell edges. And then when you, for example, you take curl of these of AWEG along this face, you get your magnetic field variable at the cell face. So, and this what is typically meant by when you say that you're evolving vector potential on a staggered grid or staggered vector potential evolution. So the first version of Spritz also underwent extensive testing. So the first quantitative check that we did was the standard test suite of Balsara Shocktube tests. and found that quite a result of their agreement in agreement with the exact solution. And on the left, you can see the benefit of implementing a staggered vector potential evolution, where in the case of a non-staggered one, we find there are post-shock oscillations, while for the staggered case, the evolution behaves rather well, matching closely to the exact solution. And this is for one of the Balsara tests. Next, we performed the standard 2D simulations of the cylindrical bus test as well as magnetic rotor, and also cross-checked our results with another code, GRHydro, and we found them to be quite matching and consistent. So for our final test, we considered non-rotating magnetized neutron star endowed with an internal colloidal field, as you can see on the left. And we evolved this configuration for with 3 different resolutions. And here on the right, you see the evolution of maximum of resonance density on the top and of magnetic field strength on the bottom. And these results do match or consistent with what is usually reported in literature. Now, the second version of Spritz also provides support for composition-dependent finite temperature tabulated three-dimensional equation of state. And it also incorporates a neutrino leakage scheme based on the Zelmani leak code. There is also an implementation of evolution equation for the electron fraction. I think there is also an inclusion of 1D Valenzuela C2P method. And we also have higher order schemes such as WENO-Z and extension of HRLE to 4th and 6th order. And Spritz is publicly available in case on Zenodo, so in case you'd like to check it out. And so the neutrino scheme is based on the ray-by-ray approach, which is used to calculate these effective rates. So, this neutrino leakage scheme is an approximate scheme, which mainly focuses on 2 different regimes. One is the emission regimes, which considers different processes like electron capture, positron capture, pair annihilation, plasmon decay, and nucleon-nucleon brainstorming. And then there is a diffusive regime, which consists of scattering and absorption reactions. For each of these processes, along each ray, using the optical depth and the cross sections of each of these processes, one can then compute the local emission rates. And using these emission rates, you can then compute the luminosity at infinity. And also, these effective rates are then used also in the evolution equation for the electron fraction. Now, we tested all of this by a set of large TOV tests, and using so you can see the table here, which considering different tests. And for instance, we used the Latimer Sveshti 220 equation of state. And for the initial data, we either considered a S slice or a T slice. It means you slice your 3D equation, tabulated equation of state, putting a constraint either as a constant entropy or a constant temperature. And then for the matter, we also start with beta equilibrium. So this reduced the 3D table into 1D1. This is for the initial condition. And then for some of the tests, we enabled neutrino leakage or disabled it. And there was temperature evolution also involved sometimes at the beginning of the test itself, or it was activated a bit later. And here I show 2D snapshots of the temperature on the top and of electron fraction on the bottom for one of such tests. And comparing here, again, the results of, on the top, you see the rest mass density, maximum of rest mass density, temperature, and also magnetic field strength for some of these tests. And we also validated our results with another code with GRHydro, and we see that we find a good match in these results. And also below, we showed the luminosity curves for the different neutrino species, and the results seem to be consistent in what is expected. So as I mentioned before, we also implemented higher order methods. So basically, precisely the WENO-Z reconstruction, finite difference reconstruction scheme. And we all performed, again, the TOV test with these higher order, employing these higher order methods. And on top right, you see the power spectrum of the maximum of rest mass density, which shows for different oscillation peaks of different oscillation at different oscillation frequencies. So here you have the fundamental mode, and then you have the overtones. And for instance, the green peak here, which is for WENO-Z plus HLLE6, is quite well captured. So indeed, higher order methods also are definitely helping to improve the accuracy of the code. Talking about convergence, we performed also a simple wave test, and we find a fifth order convergence when there is no shock present, but in the presence of shock, all the convergence goes down to first order. Now, GRMHD codes like Spritz evolve the so-called conserved variables. And as I mentioned, one needs to employ root finding techniques in order to retrieve back the primitive physical variables like density, velocities. And in literature, there exists different kinds of C2P schemes, but all could become, they could either fail or be inaccurate in certain regimes. And you could, Siegel et al. 2018, give you a good review on these different schemes, which can be based on either Newton-Raphson or root bracketing schemes. So recently we introduced a new C2P scheme, which we have in Castaun et al. 2021, which we refer to as RePrimAnd C2P. And this is based on a root bracketing scheme and shown to always converge to a unique solution. And the scheme also comes with fine grain error policies and has been implemented in a completely US agnostic way. And RePrimAnd is publicly available on Zenodo along with an EOS framework, and has, in my knowledge, been recently included also in Einstein Toolkit as an external library. And the standard version of RePrimAnd has been validated for high magnetizations and large Lorentz factors. So the next natural step for us was to implement RePrimAnd in Spritz, which we did. And I think just a moment, my slide is changing. Oh. Okay. Sorry about this. Can you still hear me?
Yes, we can hear you.
Okay, I think,
I'm online. I don't know whether the locals can hear you.
Yeah, we can hear you. Sorry.
Sorry about this. I think there is something wrong with my computer, so it's basically stuck. If you could give me a moment, I quickly reconnect in 2 minutes.
Yeah, no worries.
Okay, very sorry about this. Okay, can you hear me?
Yes, we can hear you fine.
Okay, I tried to continue. I'm really sorry about this. So I was talking about that we implemented this scheme in Spritz and performed a number of tests. So the first standard test was set the test suit of Balsara, and we found decently matching results. And then we performed again a number of 3D tests. And the first one was again repeating the TOV star endowed with an internal magnetic field, and for different resolutions again, and we found an exact match also when we compared the results with Noble et al., the C2P of Noble et al. For the next test, we endowed this TOV with an external dipolar field using the vector potential prescription of Moesta et al. 2020. And on top right, you see the magnetic field strength along with the AFI contours for the RePrimAnd case. And in general, we found RePrimAnd to be slightly more robust in comparison of the C2P implemented, the Noble C2P implemented in Spritz. And again, with increasing difficulty, we had different tests, including rotating magnetized neutron star, as well as neutron star collapse to black hole. And I found that RePrimAnd can handle these critical tests rather well. For the final three-dimensional test, we considered the Fishbone-Moncrief accretion disk system, black hole accretion disk system. And here you see on the left the rest mass density on the left, the snapshots, and of the magnetic field strength on the right. And we evolved the system for about 50 milliseconds. And here on top right, you see mass accretion rate, and below is the magnetic energy. So indeed, we find the growth of toroidal magnetic field, and this thanks to the magnetic winding as well as potential development of MRI, and this increases the magnetic energy by the order of about 2. And bottom line is that these tests help us understand that, okay, we could use RePrimAnd to handle such highly magnetized accreting black hole systems. So all this, using all these tests and the machinery in hand, we started to perform BNS simulations with Spritz using RePrimAnd. And these are the first simulations with RePrimAnd and Spritz, which for the first test, we started by the simple initial data, that is an equal mass system that has also been adopted by Ruiz et al. And we use ideal gas equation of state for evolution. And for resolution, we have the finest resolution of about 350 meters. But then just before black hole formation, we activate another refinement level of about 180 meters, finer refinement level. And after about 2 orbits of evolution, we paint the 2 neutron stars with dipolar fields that are extending also outside the surface, as you can see on top right. And then along with that, we add a very low density material that co-rotates with the system, which following Keplerian profile. And this co-rotating gas or material has involvement only in the beginning, because since it allows the magnetic field in the atmosphere to co-rotate with the system, and later on you have the ejecta that's coming out, and then that takes over in these regions. So this co-rotating material is added for till about 950 kilometers radial distance. So here you see the movies of rest mass density on the left and of magnetic field strength on the right. The merger produces a hypermassive neutron star which survives for about 8 milliseconds before collapsing to a black hole of mass of about 2.9 solar masses and having a spin of about 0.8. And this is surrounded by an accretion disk of mass of about 0.06 solar masses. And towards the end of the simulation, we find the system to have reached steady state accretion with the disk mass of 0.03. And meaning that the accretion times this will be an accretion rate of about 0.11 solar mass per second, which gives us a rough accretion time scale of about 300 milliseconds, or the full disk will be engulfed by the black hole. Looking at the magnetic field topology, we find that soon after the dipolar fields are imposed, they start to feel the presence of the turbulent material. And on the right, we have, so we evolve the system for about 50 milliseconds after merger. And at final time, we find that there is indeed toroidal amplification close to the equatorial plane and growing helical structures along the spin axis, which could act as an ideal site for jet formation. Looking at magnetic field evolution, magnetic field does get amplified due to different mechanisms in action. So at merger first, Kelvin-Helmholtz develops in the shear layer when the two neutron star cores come into contact, and later on, magnetic winding plus the potential development of MRI continues to amplify the magnetic field and after the collapse. But by the end of the simulation, we find that the magnetic energy is still growing, but it's not likely enough to power a relativistic jet yet. And on top right, you see the snapshot of magnetic to fluid pressure ratio. And we find that this ratio is about 10 to the power minus 4 along the black hole spin axis.
10 minutes.
So clearly this system, this funnel along the spin axis is fluid pressure dominated, and below you see a snapshot of the radial velocity showing that the matter is rather inflowing rather than what you expect in a jet, like an outflow. So comparing our results with that of Ruiz et al., we find that they start with a really large magnetic initial magnetic energy, and the corresponding initial magnetic to fluid pressure ratio is of the order of at least 200 times higher than in our case. They also employ a much higher grid resolution as well as compared to what was in our case. So using their results, we tried, okay, let's try with a much larger initial magnetic field. So currently we have 2 simulations ongoing, and they are still work in progress. And one is a low resolution one, which is still ongoing, and it has reached collapse, while there's another one which starts with a slightly lower magnetic, about factor order 1 lower initial magnetic energy. And it's already showing some promising results. So so I'm talking about the high resolution one. And here you can see about 47 milliseconds after merger, there's a growth of helical structure along the spin axis, and there's also some kind of outflow that's coming out. And this, the funnel along the spin axis is magnetically dominated, where magnetic to fluid pressure ratio reaches about factor of 10 in certain regions. And at later times, the helical field is developing, and the outflow becomes a bit more faster. But it still has Lorentz factors which are much lesser than 1.2, so it doesn't represent a jet yet, or an incipient jet is what is defined in Ruiz et al. 2016. But the beta is also slightly increasing in time. Apart from these results, there are also different projects with Spritz currently ongoing. So Lorenzo Enochi at RIT is working on a project comparing as a code comparison project between Spritz and Illinois GRMHD. This is based on BNS simulations. And at University of Milano Bicocca, we have master students of Professor Bruno Giacomato who are working on BNS simulations with the BL-hot equation of state using either Loren initial data or Karat initial data. And we have Rahim Mathur from AK University in Turkey, who is working on black hole neutron star simulations, Spritz versus comparing Spritz versus Visky-Tietty using DD2 equation of state and cut out initial data. With that, let me quickly summarize. Spritz is a new state-of-the-art GRMHD code with neutrino emission reabsorption, still a carpet-based code. Then we also have this new RePrimAnd C2P, which has shown to be quite accurate, efficient, and robust. Now we recently are working on the first BNS simulations with Spritz and RePrimAnd, which is able to handle highly magnetized black hole disk environments. And what we learned while comparing our results with Ruiz et al. 2016 is that we need to start with ridiculously high initial magnetic energies for the adopted resolution. And if we want to see some kind of outflow or kind of incipient jet production. For future exploration, we're still working on using temperature and composition dependent equation of state. And at some point, we have to also activate the neutrino radiation in the projects that I talked about, which are using realistic equation state. And then also we would like to include neutron star spins. With that, I stop here. Thank you very much.
Thanks so much, Jay, for that wonderful overview. Do we have any questions? Just to clarify, the BNS simulation you showed, and perhaps maybe all of them, I'm not sure, but did they include neutrino?
5 minutes.
Are you muted?
Oh, sorry, I was muted, right.
Yeah.
Yeah, so these simulations do not use neutrino radiation. They just use a typical ideal gas equation state, very simple setup. Because one of the reasons why is that with RePrimAnd, we are still building the support for providing to use the realistic temperature and tabulated equation state, temperature dependent tabulated equation state. So it is still not ready yet in my knowledge. So once that is ready, we would like to also, of course, use realistic equation state and then also use neutrino radiation. That's the future goal.
Cool. Also, yeah, Manuela has a question. Go ahead, Manuela.
I raised my hand when you were asking a similar question, but I had a really similar question, Zach, except that maybe I'm interested about the particular magnetic field topology that you have shown, Jay. Is that also the same? It's the answer that you gave to Zach is also the same for that particular run that you showed about the magnetic field topology, the geometry of the field.
Yeah, exactly. It's the same. So we don't have we are using this prescription by Moista et al. For this dipolar field.
Yeah.
Extends also outside, and we add some material so that it can co-rotate. But this is for the equation of state, we are still using the ideal gas equation of state, and we don't have any neutrinos or finite temperature.
All right.
Yeah.
Thank you.
Thank you.
Yeah, Matt has a question.
Yeah, do you have to do anything special to make the magnetically dominated region behave in the magnetospheres? Your MHD code just work?
Sorry, could you kindly repeat the question?
I can repeat. Yeah, no problem. So in the magnetosphere, where you're in a very magnetically dominated region, do you have to do anything special to ensure that the dynamics are reliable?
Right, exactly. So what we do, and probably I'll explain this with this plot below, is that we add some low density material. This is only initially, and this is radially distributed and then follows also an exponential decay profile. But for the rotation of this material, we try to match, we add a, make it follow a
2 minutes.
Keplerian profile. So it starts when the magnetic fields are added. This is after 2 orbits. And the material is also added at the same time. So the magnetic field in the atmosphere can also, as the fluid moves in the atmosphere, the magnetic fields could also move. But this is just initially. Later on, you would see that all the ejecta that comes out from the merger actually takes over this co-rotating material, and then magnetic field follows the ejecta essentially because of the ideal MHD prescription assumption that it works on. But this is just initially just to make the magnetic field co-rotate in the beginning.
Matt says thanks.
I actually have.
Yeah, Leo has a question.
I already looked a little bit at Zelmani leak, and I would like to ask, what do you think would be the challenges of moving from
1 minute, please conclude.
to a binary neutron star system with that particular code?
Could you, so I heard something about Zelmani leak. Could you kindly repeat?
Yeah. So we understand you use a Zelmani leak for the neutrino leakage, right? The question is, and you showed some results with using the Zelmani leak and neutrino leakage prescription with TOV stars.
That's
Leo's
correct.
question: how would can you
30
comment
seconds.
on how that might be extended to the binary neutron star case?
Oh, that's a good question. So since it follows a ray-by-ray approach, it might be difficult. We are still thinking about this. So it might be that once you have the hypermassive neutron star, it's much easier to include this, incorporate the leakage. But I think I'm not sure if Professor Giacomas or anybody else has already thought about how to include this when you have the 2 neutron stars approaching merger. So you can activate that already. That time. Definitely you can activate temperature evolution before that, because you need that for before the leakage scheme is activated. But yeah, that's something that would be also beneficial during the hypermassive neutron star phase, or also when you have accretion disk formed. One thing that would be also interesting to check is that Zelmani leak is a ray-by-ray approach. So if there is a kick to the black hole, you need some kind of you need to track the black hole so that the calculation, which is a ray-by-ray again, should follow the system in hand. That is something that has still to be implemented, but it should be easy to implement. We're not there yet, but we are close.
I think Bruno addressed the second question, because I think the pre-merger would be very hard, but I think even the post-merger is still suboptimal.
Yeah.
Okay, thank you.